Okay, apologize. I wasn't watching time. So we were on this slide talking about this idea again of this negative charge relative. So the outside is positive, inside is negative. These negative aspects comes from proteins, sulfates and phosphates, and they are inside and can't move outside. And so we've got this, again, distribution of potassium, sodium, calcium, as well as many, many negatively charged ions. And this results in, again, at rest, no changes occurring, nothing happening, of about minus 70 millivolts. All right? So keeping an eye on this, again, time on the x-axis. So the action potential is an electrical signal, and action potential is going to result from electrical change. So this resting potential would remain and nothing would happen unless there is some change. Okay? And the change is going to be in the distribution of sodium in this circumstance, though it's not exclusively what can happen, but we're going to start off with, causing an action potential. And key to that is sodium. So a channel for sodium opens. Again, we're not stating is it ligand gated or mechanically gated or a leakage channel. All right, we're just saying, or voltage gated. We're just saying a channel, because I'm really not interested in testing you on knowing all the different types of gated channels. We mention them in the book, and it's important to know that there are a variety of different ones. We're just going to now use generically a channel, a sodium channel or a potassium channel. So a channel for the sodium ion opens, all right? This concentration gradient with high sodium outside of the cell and low inside means that sodium starts to enter, okay? So as it starts to enter, we see this change, all right? So we're going along, no changing occurring, and then here we start to open sodium channels, all right? So the charge inside becomes less negative. So going from minus 70 to minus 55 in this circumstance, but through gradations of, minus 60, minus, 65, minus 60, and so forth. This change from a more negative to a less negative gets the term depolarization, doing away with the polarity. I said there is so much sodium coming in that the membrane inside actually becomes positive if this continues relative to the outside, and you see that here. So this is the depolarization event that is due to the movement of sodium, and that's what's key for you guys to know, that sodium ions, which are high outside, are now coming in to the cell. And as they come in and bring their positive charge, this difference between the inside and outside, here at 0 there would be no difference, but so much sodium comes in that it actually becomes more positive inside the cell membrane relative to the outside. All right? With the positive charge inside, this triggers the opening of potassium channels. Okay? So potassium channels, right, open right about here. Since potassium is positive also, but it's high inside, if you open the channel, potassium will start moving out of the cell. So it starts to leave, which means now we are restoring this, right, this idea of positive outside and negative inside, right? So positive, again, potassium leaving, so now the inside of the cell is becoming more negative again, and we call that repolarized. So we're resetting or re-establishing this polar, right, positive negative difference. All right, so I say again, what started all the channels opening? This is our question now. So why did we get this and why did we get this, right? And I remark here that there's different channels we discussed a few slides back and what they responded to. So again, we could have gotten the channels opening because of a mechanical change or a ligand gated like we did in the muscle. And this change is definitely from a voltage here. And what's occurring here is part of leakage channels, okay? So, and just to finish out, the hyperpolarization comes from the fact that so much potassium will be leaving that you actually get it goes even more negative than it was at rest. But then it reestablishes with the, again, potassium coming back in and into the cell, and so we get back to our resting potential. All right. So here we are looking at this now. Here's our last figure. We're just adding the neuron to it. So threshold, again, we had this back here. Threshold is actually minus 55. So threshold is the minimum requirement of change. I said change is change, again, and change in electrical potential. So what does this change represent from minus 70 to minus 55? Well, there's a certain number of sodium channels that have to open if the neuron is going to respond. All right, so here that's what we see. So in the first figure here, we've got one, right, axon coming down and causing the sodium. In the next one, we see 3 of them. So with only one sodium, one axon releasing its neurotransmitter and opening a sodium channel here in the membrane of the cell body, we don't have enough of a change. See, so here's our minus 70, and we needed to get to minus 55. But the change wasn't very much because we didn't open many sodium channels. All right? In the second scenario, we've got a number additional axons releasing neurotransmitter and more sodium channels opening. And in this one, we do meet the minimum requirement. Enough sodium channels open, so enough sodium starts to enter, and we get this depolarization. Okay? So again, I say here that initially depolarization results in a local potential. So this is local, just here, right? As opposed to an action potential, which is going to be generated here in the axon. All right? If there's not enough change occurs in this membrane potential, right, which we're measuring here, nothing happens, no action potential. If you generate enough of a change, as you see here, then you reach threshold and you will start an action potential. So again, we're looking at here, they're actually measuring, giving a measure, this change here, excuse me, these two here, sorry, I missed that one there, but there's only 2, and the amount of sodium that enters is not enough, right, because we only get a minus 62 as about the, right, maximum. Here, by adding one more, right, axon causing another sodium channel to open, we reach threshold, minus 55, and we trigger an action potential, which is going to move down the axon. All right. So a little bit about these action potentials. They are considered all or none. So if you hit threshold, the change is going to occur, and every single time the change will be to about plus 30. So more intense stimuli, so hotter water, deeper pressure, right, more forceful, is not going to cause, right, more sodium to enter. What it's going to cause is going to cause this change to be more frequent. So the frequency of the change is going to increase, and that is going to be translated by the brain into an increase in the stimuli. So stronger stimuli increases the frequency, but not the magnitude, right, which is plus 30 here, of the action potentials. So again, all or none, if you hit that threshold voltage, which again is really representing the number of sodium channels open, the charge reversal, right, with the outside becoming slightly negative to the inside, will occur, and action potentials will be generated. The action potential will be the same magnitude always. All right, this is really quick. I want you to think about how quickly you respond to things. So 2 millisecond window, right, thousandths of a second. So the change necessary to start and transmit electrical signaling or communication is so quick, all right? And this is what allows us to survive, though, this quickness, right? Okay, there is a block to process, right, becoming tectonic, and this is called the refractory period. So you won't have this, right, tectonic stimuli like we talked about when we looked at force over time in the myocyte. There is a refractory period. Refractory period is the time in which you cannot stimulate again, right? I say here there is an absolute and a relative refractory period. During the absolute refractory period, another action potential cannot be started. And I said the reason for this is that the sodium, right, sodium gates have been inactivated, so they can't do anything, And this blocks sodium moving until the membrane falls below negative 55 at this point. All right? When you reach minus 55, the relative period, right, so I said absolute and relative, allows opening and depolarization, but you need a stronger stimulus because your potassium gates are still open at this point. Okay? Now, I'm going to tell you this right now. I'm not actually going to ask you about the different types of refractory periods. It is an important concept, but really as you go on, right? And again, absolute, you can't generate, that's really what I expect. You cannot generate another action potential. A relative, you could with a strong enough stimuli. All right, now, moving along. So we got our action potential. It started at the axonal hillock. When we look back here, okay, and we see it here. Now, what's going to happen all the way down this axon? And remember, you have some pretty long axons in your body, right? But regardless of the length of the axon, the same thing is going to happen. If we've hit our threshold and we've started an action potential, it's going to have to move down this axon. And so we say we start at the initial segment or axonal hillock. There are lots of voltage-gated sodium channels. And so they're responding, they're opening because of that threshold, that change. And as they open, it shows you here, positive coming in because sodium's out here, right? This is the inside, this is the membrane shown as a tube. The absolute refractory period means that the sodium channels, so here's where it's important to understand this, means that the sodium channels which have just been opened cannot open again, and therefore the action potential goes in one direction. So again, just helping to clarify for you guys who are really, wondering. But again, I don't see any point to elaborating and asking test questions on refractory periods. Okay, but that's the reason why you're going to get it going in one way. All right, it's going to move down, not backwards, back up. All right. When myelinated, right, and again, this shows you that it's going to keep moving along. So the change that occurred here is going to stimulate a change here, right? Sodium's going to come in here. The change here is going to stimulate a change here, and all the way down. All right. Now, if the axon is myelinated, then the change actually only has to occur at the gaps. And by the way, it can't occur where there's myelin because myelin is an insulator. It is preventing a change, right? So lots of lipids excludes water and prevents most of the flow of ions. So it's an insulator, right? So if it was a solid, right, block, you wouldn't be, action potentials wouldn't perpetuate. They wouldn't move down here. But because there's gaps, and these, right, we said the myelin, the sheath, it measures about 1 millimeter on the axon, and then there's a gap, and 1 millimeter or 2 millimeters, and a gap, right? So these gaps are sensitive to these voltage changes, and so the voltage change here is close enough to this membrane here that it triggers, right, the opening of sodium channels, as you see here. And this difference is close enough to this one, which triggers the change here. So the potential doesn't have to move all the way down, right? Opening and closing, opening, closing, opening, closing, opening, closing. It can open here, open here, open here, here, and so it moves quite a bit faster, and we call that the saltatory conduction. So the action potential doesn't have to travel the entire length of the cell membrane. It has to go the entire axon length, but not every single segment of the cell membrane. All right, graded potentials. Let me actually stop the video here because we're kind of at a convenient place and pick this up on the next video.